devices. So let's talk about me. My name is Ivica Bogosavljevic. I'm an application performance specialist. My professional focus is application performance improvements. The techniques you can use to make your C++ program run faster, either by using better algorithms, better using the underlying hardware, better usage of the standard library, compiler, programming languages, or the operating system. I work as a performance consultant. That means that when development teams have problems with performance, they ask me for help. I also write for a software performance blog called Johnny Software Lab. The link is in the footer, so it's here. Feel free to go visit and subscribe either through Twitter or LinkedIn. So, an introduction. Well, in today's world, battery-powered devices are ubiquitous, and that means that it is important how we write software for them. The fact that they're battery-powered puts some unique requirements. The main goal is to save energy, so performance is important, but if your application consumes too much energy, that's bad. Now, we will answer the question on how does performance go in hand with battery life. In this talk, we will give an overview of the following. How does performance go in hand with battery life? So, when is the performance good for battery life and it's not? General software design principles for battery-powered devices. How to write software that works fast and doesn't consume too much energy. Performance optimization techniques. So what techniques are applicable to mobile devices, which are not. We'll also give some ideas on how to optimize computational intensive codes and memory intensive codes. About the computational and memory intensive codes we'll talk a bit later. Before starting, we need to have a model on how CPU uses battery. So a CPU often consists of several CPU cores. Typically 8, for example, my phone has 8 CPU cores, and this CPU core can be either running at full speed or sleeping. So this is not exactly true, but it's mostly true. When running, it consumes full power. When sleeping, it consumes very little power. Now, the core, how does the core work? It wakes up, it does some useful work, and then it goes back to sleep. What we want to do is keep it in the sleep state as long as possible since this decreases the battery consumption. Performance is important even for software that doesn't have an explicit performance need. Faster software makes the CPU core spend less time in running state and more time in sleep state. Now we talk about designing components on the API, on the component API. All the data you're processing should happen at once. Your component processes the data, when it's done it goes to sleep. You should not wake up your component too often. So if your component has a thread which wakes every millisecond, you should increase this time interval to 100 milliseconds or 1 second. You should avoid polling. So what's polling? Polling means that your component goes and asks another polling to check if it's done or if it has data that the current component needs. So you should avoid it. Instead, you should use events, and you register for the events when the data is ready, and when this race, your component is informed about that. Also, when you're designing your component, you should design with events. Next thing, you should avoid chatting with either local components that are in the same memory space or remote components over TCP/IP. So what does chatting mean? Chatting means that you exchange a lot of messages between your component and other components. So your component exposes some API, or the other components also expose its API. So the two components, when they communicate, they should communicate in the least number of messages as possible, so ideally one. And the last thing, which is also important, is you should strive for high performance processing. So high performance processing means that your CPU will be fast, and will be done with its work sooner, so it can go to sleep mode and it can save battery time. So what is the way of the performance on mobile devices? So in high performance or desktop settings, one of the ways to increase software performance is through multithreading. So multithreading means that you distribute your work to several CPU cores. This often increases performance. However, on mobile devices, this is often not a good idea for several reasons. First, multithreading increases energy consumption. So each CPU core that is running consumes energy. Next thing, multithreading is difficult if all cores are not equally fast. So in mobile devices, you often have a situation when some cores are faster but use more energy, and other cores are slower but use less energy. And this can be a problem because load balancing is more difficult, although not impossible to make. On mobile devices, all CPU cores share the same bus over the memory, and if this bus is used too often, if it's saturated, that means that CPU cores will most of the time wait for the data. They won't be doing anything useful. And while waiting for the data, they will consume energy. A well-written single-thread program algorithm can outperform an ably written multi-threaded algorithm. This has been proven several times. However, multi-threading of a well-written algorithm doesn't necessarily have to mean an increase in energy consumption. So you can have an algorithm that is using several CPU cores, but if it scales well, that doesn't necessarily, if it scales well, that doesn't increase battery consumption. So if the time your algorithm takes is 10 seconds and on one core and 2.5 seconds on 4 cores, that is a perfect scaling. So this scaling to several CPU cores doesn't increase memory consumption in this case, but battery consumption in this case. At the end, measurements will tell you if multi-threading is a good idea or not. We talked about how to better use hardware resources. So for peak performance, you want to write your program so it uses hardware resources optimally. Now, from the viewpoint of hardware resources, there are two major bottlenecks. The one bottleneck is in the resources on the CPU core. So if the CPU core have enough data, but they cannot process it in die, then we say that the program is core bound, and that the program is computationally intensive. On the other hand, if you have a program which is limited by the amount of data it needs to transfer from the memory, so if the CPU core is waiting for the data from the memory, we call these codes memory intensive, or we say that the code is memory bound. There are different optimization strategies that you can use for computational intensive and memory intensive, so they're completely different. Which asks another question: is my algorithm or my program computational intensive or memory intensive? Now, to find out, there are several tools, profilers that you can use. For example, Intel's VTune, AMD Microprof, PMU tools, Perf or Liquid. And these tools can read special hardware performance counters, and from these numbers you can figure out if your code puts more pressure on the memory subsystem or on the CPU subsystem. Memory intensive codes will typically have bad numbers in the memory bound section. So these tools have two sections. One is called memory bound and the other one is called core bound. Memory bound, and you should focus on the data cache miss section. When the data cache miss section is bad, that means that your program is memory intensive. Now, computational intensive codes will typically have bad numbers in the core bound section. That means high usage of various units of the CPU, like vectorization unit, divider, large amount of branch misprediction. So these tools are complicated to learn. It takes time to learn them, but on the good hand, sometimes there are simpler ways to determine if your code is computational intensive or memory intensive. Optimizing computational intensive codes. Is my code computational intensive or memory intensive? So your code will be computational intensive if it is processing simple data types like integer, chars, or doubles. So the data is stored in an array or vector, so it's array or vector, not hash maps, not binary trees, so on. And you're accessing neighboring elements of the array sequentially. So you're looping over an array which goes from 0 to n, or from n to 0, and it decreases by 1. So you're accessing elements of the array 0, 1, 2, 3, 4, 5, and so on. If you are accessing every second or every fourth element, like 0, 4, 8, and so on, in that case your program will most likely be memory bound, not memory intensive, not computational intensive. Computational intensive codes are often found in domains like image, audio, and video processing, machine learning, especially linear algebra, telecommunication, scientific computing, and others. On most other occasions, you can consider that your code is memory intensive. This is especially true if your code is processing classes, even more so if classes are large. So if your code is processing classes, even if they're stored in an array, it is probably memory bound. Slide is about fixing memory intensive codes. So we prefer to be computational intensive more than memory intensive. Why? Because memory is slower than the CPU. So every time if your code is memory intensive and if there is a way to make it computational intensive, that is the right way to go. So there are some transformations that you can make to make your memory intensive code computational intensive. So let's talk about these transformations. There are two of them that I'm mentioning here. One is called structure of arrays. So if you're processing instances of classes in a vector, you can benefit by changing the class memory layout. So how does that look like? Here's an example. So we have a class student, and it has a name and an average mark. And then we have a vector of class student. Now when we convert it to structure of arrays, we have a class students, and then each member from the original is stored in a separate vector. Does this help? So if you want to calculate the average mark of all students, original code takes 194 memory seconds, and when converted to structure arrays, it takes 42 milliseconds. That's the first technique, structure of arrays. Next technique is called loop interchange. So if your program is processing data in a matrix, and it is running through the matrix column-wise. So there is a matrix, but you're not going row-wise, you're going column-wise. Your program is most likely memory-bound. And how you can fix this? You can fix this by performing a transformation called loop interchange. So look at this code. This is the original code, and this is the code with the loop interchange. So look inside. C of aj equals C of aj plus A of ik times B of kj. So with regards to the innermost loop, which goes over k, so this is a constant because k doesn't take part in this expression. This is also constant. This is going row-wise through A, but this here is going column-wise through B. Now, if we perform the loop interchange, the loop over k goes outside, and loop over j goes inside. So, with regards to the innermost loop, this axis is sequential, so row-wise. This is also sequential row-wise. This axis is constant; it doesn't depend on j, and this axis here is also row-wise. So we have 3 row-wise and 1 constant. And originally we had 2 constant, one which was row-wise and one which was column-wise. So with this transformation, this program is accessing memory locations sequentially. I tested this with matrix size 1200 times 1200. The first loop takes 5.8 seconds. The second loop takes 1.22 seconds. The talk until now was a talk on how to fix memory-intensive code, how to convert them to computationally intensive codes. Next, we'll talk about vectorization. So vectorization is important concept or important thing if you want peak performance, if you want best possible performance. So many modern CPUs can process more than one data in a single instruction. So more than one piece of data in a single instruction. This model is called SIMD, single instruction multiple data. So these are special instruction, and one instruction can, for example, perform 4 loads, 4 adds, or 8 adds depending on the type. Now the compilers are smart and can automatically generate code that uses SIMD instructions if certain conditions are met. So look on the left side, this is the loop written in C, and when the compiler so this is a loop written in C, and this is a simple loop, calculates B of I plus C of I. A of I equals B of I plus C of I. So it adds together 2 vectors and puts the result in a third vector. So with autovectorization, how does that look like? First, the loop goes I++ here, and here we see that it goes over 4 elements of the vector. So this is some kind of pseudo assembly. So it loads 4 elements to a register of vector B, then it loads 4 integers of vector C to a register, and then it adds them together, and then it stores them back to the memory. So all the times you're working with 4 integers, not with 1 integer, as one might expect when looking at the original source code. So vectorized code typically runs 2 to 6 times faster than its non-vectorized counterpart. The compilers can auto-vectorize loops when some conditions are met. If the compiler has auto-vectorized a certain part of code or a hot loop in your code, it's a good indication that your code is running at maximum possible speed. Now, if you want to check if the compiler has vectorized your code, you can use some compiler flags. On Clang, this is the compiler flag. On GCC, it's a different one. Even if your chip doesn't support vectorization, the fact that the compiler vectorizes your code for some other architecture that does is a good indication that your loop is using optimal the chip's resources. So a code that is vectorizable is efficient code even on those architectures that do not support vector instructions. Although nowadays most, if not all, CPU support vector instruction. So what are the prerequisites for autovectorization? The most important one is a good memory access pattern. So you want a loop that goes over an array or a vector from 0 to n, or from n to 0 with a stride 1, so e++, not e plus equal 4. Next things you want to do is you want to have independent iterations. Independent iterations mean that each iteration can be done by itself. It doesn't depend on previous iterations. So if, for example, if you have a loop, if you can run it from 0 to n or from n to 0 and that doesn't change the results, then you have independent iterations. In case the data for the current operation depends on the previous iteration, we say that the loop has data dependency and it is difficult if impossible to vectorize. Sometimes it's possible with some tricks. Next thing is that number of iteration is known before the loop starts. What does that mean? If you have a for loop, that means that you cannot break out of it. You cannot use break, you cannot use continue in the loop, because that means you're skipping over some iterations. And also the start and the end should be constant during while the loop is running. So the start index and the end index should be constant. Loop that goes from 0 to n is a constant, but if n changes inside the loop, then it's not constant, and we say that the loop is not, the number of iterations is unknown. Inside the loop body, you should not have a lot of if statements or switch statements because they make vectorization more complex. The nature of vectorization is that your program is doing the same kind of instructions on the data. It does, for example, 4 adds. Now, if you have, in some cases you want to do add, but in some cases you want to do subtract, in that kind of loop vectorizes poorly. Last thing is there should be no pointer aliasing. So if you have 3 arrays A, B, C in the loop, and you're processing a loop, so pointer aliasing would mean that A and B point to the same piece of memory. If that is the case, then the compiler cannot auto-vectorize that loop. If your critical loop doesn't vectorize, you can try things to fix it. For example, if the loop doesn't vectorize because it has too many conditional or it's too complex, then you can split the loop into 2 loops, one which is vectorizable and one which is not. Also, if you have inside the loop, if you have a condition which is loop invariant. Loop invariant condition means that the condition, when you enter the loop, the condition doesn't change. It's always true or always false. Then you can try an optimization technique called loop unswitching to fix it. If you have break statements in your loop, then there is a technique called loop sectioning that can help you enable vectorization. If you have a bad memory access pattern, then you can apply the techniques we talked earlier, so converting to structure of arrays or loop interchange to improve memory access pattern. If your loop has pointer aliasing or the compiler is not sure if 2 pointers alias each other, you can use the restrict keyword to mark pointers that are independent of one another. So you should enable compiler optimization report, vectorization report, and it will tell you if you are moving in the right direction. When you see the loop is vectorized, then you have achieved your goal. If the compiler automatically vectorizes, that's a pretty good indication that your code is running at peak performance. Now we talked about optimizing memory-intensive codes, and this is a completely different story compared to the computational-intensive code. So how does that go? So in modern systems, CPUs are much faster than the memory, and CPUs often have to wait for data to be fetched from the memory. So the CPU designers had a small fast memory called the data cache memory close to the CPU. And this memory is used so CPU can keep data it accesses often in this data cache memory. Access to a piece of data which is already present in the data cache is fast. Access to a piece of data which is not in the data cache is slow, because it needs to go to the main memory. Many programs, especially those written using object-oriented paradigm, so classes, use memory inefficiently. And programs that are aware of the way memories work can use this knowledge for more efficient access. When do data cache misses typically happen? So when we're optimizing memory-intensive codes, we want to use data cache memory as efficient as possible because this translates to a faster access. Data cache, we want to increase data cache hits or we want to decrease data cache misses. So when do data cache misses happen? They typically happen when you are dereferencing a pointer for the first time, which is a very common operation using operator arrow. If you have a class and inside it you have a pointer to another class, every time you access the other class through a pointer, you will most likely have a data cache miss. If you're accessing for the first time heap allocated objects, heap allocated classes. If you have a vector of pointers, so vector, either raw pointers, shared pointers, doesn't matter, which are typically used for polymorphism, every time you access an object to a pointer, you'll get a data cache miss. Lookup in as std map, std unordered map, std set, std list, so all tree-based, linked list-based, and hash map-based containers. Lookup will have a lookup inside those containers will typically result in data cache misses. Iterating through std list, std map, or std set will also most likely result in data cache misses. If you're accessing a member of array or another data structure in a random fashion, so this is called a histogram loop. So there is this array histogram, but we're not accessing it with I. We are accessing it using index from A of I. If this array A holds random numbers, then you'll get each access to this histogram array will result in a data cache miss. Also, binary search will typically result in data cache misses. So if you have a sorted array and you're doing binary search on it, every time you go accessing a member of array to check if it's bigger or smaller, then you'll have data cache misses most likely. So this is when data cache misses happen. When do data cache hits typically happen? So if you're iterating through an array or vector sequentially, so you have an array or a vector, and you're iterating through it, you will have data cache hits. So the smaller the type, the higher the chance of hits, of cache hits. So if you have a small type like doubles, floats, integers, so on, it will be less data cache misses. If you have like large classes, it will result in more data cache misses. There is a number one rule of peak performance. Peak performance is achievable only when working with arrays and when you're iterating through them sequentially. Next thing is keeping the data set small. If your data set is small, if you have a small hash set or a small hash set, a small binary tree, it will be faster than the large data structure. Next thing is what is accessed together should be close neighbors in memory. So if you have a class and inside it you have two data members that you're often accessing together, then you should declare those two members close to another in memory. You should declare them close to one another in the in the class definition. Next thing is what is accessed one after another should be laid down in memory one after another. So take an example of linked list. So in linked list, if you have two nodes that are neighbors, so the second one goes after the first one logically. If you put them in memory one after another, you'll get a good performance and you decrease the chance of data cache miss. Or for example, a binary tree. If you have a binary tree, you have a parent and left child and right child. So if you put parent and the left child close to one another in memory, every time your program has to take the left child will be probably in the data cache, and this decreases the data cache miss rate. So how do these recommendations translate to everyday development? Here we give some general recommendations of the things that can increase or decrease data cache hit rate. Here's some common example, and we give also the numbers. With performance, you need to have in mind that you should always measure performance. You should never guess. So first example is minimum and maximum in the array. So we have an array or a vector, class size 16 bytes, 100 million elements. What is the time needed to find the minimum and the maximum? If we are doing in the same loop, or we are doing first loop finds the minimum and second loop finds the maximum. So if we are using the same loop, it's 207 milliseconds, and if we are using separate loops, it's 368 milliseconds. So where this difference comes from? So in the case when we use separate loops, we iterate over the same data set 2 times, and this wastes memory bandwidth. So what is the conclusion? What is the rule of thumb? Do as much work as possible while iterating over a data set. So you should never iterate over a data set 2 or 3 times. STD offers STD min-max to find both minimum and maximum at the same time. This was the first example. The second example is linked list memory layout. So we have a linked list. and these are nodes, and these are pointers. So this linked list has six nodes, 6 values, and we have 3 memory layout. The first one is called random memory layout, because the nodes are just stored randomly in memory, so there is no pattern here. The second is called compact memory layout. In this case, the nodes are compact in memory, so they're not dispersed through memory, but again there is no pattern accessing. So if you go like this, you're just jumping around memory when you're going through the linked list. And the third one is called the perfect memory layout. Why is it called perfect? Well, first, the nodes are compact in memory, and second, logically neighboring nodes are also neighbors in memory. Which layout is the best for iterating over the list? Let's see. So we have 3 layouts: random layout, compact layout, and perfect layout, and we have 3 linked list sizes: small with 128 bytes, medium with 1 million bytes doubles, and large with 64 million doubles. So for the small linked list, the layout doesn't matter. See, these numbers are the same. But for medium and large, the perfect layout is much, much better than both compact layout and the random layout. Compact layout is, on the other hand, faster than the random layout. For a large linked list, perfect layout is 125 times faster than the random layout. Now, you can control the memory layout using a custom allocator. So why is the perfect memory layout the fastest? The CPU has a component called the data prefetcher. So data prefetcher is a component of the CPU that can figure out your program's memory access pattern, and then it preloads data. It loads the data from the memory to the data cache before the CPU even needs it. For arrays and vectors, figuring out the memory access pattern is typically trivial if you're going sequentially from one side to another. And if you want fast processing, you should use arrays or vectors. So this is the reason why data access is so much faster with a perfect memory layout. The data prefetcher can actually preload all the data before it's even needed. Okay, next example is vector of pointers. So vector of pointers appear often because they enable polymorphism in C++. We have a vector which is holding the pointer to the base class. Now, vector of pointers itself is just a block of memory, but each of these classes is allocated on the heap. Now again, you have 2 layouts. This is an optimal layout, where neighboring pointers point to the neighboring instances in memory. This is the optimal layout. And the second layout is non-optimal layout. So we have here that neighboring pointer just point to random classes in memory. Now again, same as with linked list, there are performance implications when the layout is not optimal when you are iterating over the container, over the vector. So what are the performance of vector of pointers? If we are iterating through a vector of 20 million objects, if the layout is perfectly optimal, it takes 384 milliseconds for small virtual function. For non-optimal layout, it takes 5 seconds. If the virtual function is large, it does many computation, it's slightly better. It takes 2.6 seconds for the perfectly optimal and 16 seconds for the perfectly non-optimal layout. So here we have speed difference about 30 times, and here we have speed difference about 5 times. So the problem of memory layout becomes apparent again. You should strive to avoid vector of pointers whenever possible. Vector of values are much better for performance compared to vector of pointers, and not only because of the data cache hits and data cache misses. First thing is that all memory is allocated in a single block. So with the vector of objects, we have a single block of memory. That means less calls to malloc and free. Next thing is the sequential access to objects translates to sequential access to memory addresses. And the CPU prefetcher can work well in these situations. So there are no calls to malloc and free. There is no virtual dispatching mechanism to slow these things down, although virtual dispatching is not that, doesn't account for the difference. So the main difference comes from data cache misses. With vector of values, small functions can be inlined because the type is known at compile time. The downside is no polymorphism. If you want speed, you should prefer vector of values, and it is possible to implement array of values with polymorphism. You can find more information here. So if you need polymorphism, you can find information how to implement this without data cache misses. This was a talk about layout for the vector of pointers. Now we're going to do an experiment with class size and member layout. We have a class here called rectangle. It has three members: bool visible, padding 1 and padding 2. Visible, point 1 and point 2. It also has these two members called padding 1 and padding 2, but their size is compile time constant. We use this padding 1 and padding 2 to change the size of the class rectangle. We want to measure how the size of the class actually influences the performance of the program. We have this function called calculate surface visible. So what does it do? It goes through a vector of rectangles, and if the rectangle is visible, then it adds its surface to the overall surface. So it calculates the surface of all visible rectangles. Okay, this is the one function. There is another function that calculates the surface of all rectangles. It's same as this one, except it doesn't have this check if the rectangle is visible. So how does the speed of processing data depends on the size of the class? So the red one is the calculate surface all, and the blue one is the calculate surface visible. Now see, when the class size is really small, the smallest 20 bytes, this is when it's fastest. As the class size grows, the speed of processing slows down. You go here from 30 or 40 milliseconds to 150 milliseconds when the class size is 500 bytes. On the calculate surface visible, originally takes 110 milliseconds, and as it grows, the class size grows, so the processing slows down to more than 200 milliseconds. What we wanted to do here, which was interesting to do, we have visible, we have point 1 and point 2. So surface is calculating by multiplying point 1 by point 2. And we have this visible, point 1 and point 2. And in this function, we are accessing visible, point 1 and point 2 together. So we have this padding 1 and padding 2. Now we want to see, even when the class size is constant, but there is a padding between these two elements, visible and P1 and P2, does that influence performance? So we want to check if we are accessing these two members together, and we want to check if laying them out in the data in the class one after another, does that have any influence on the performance? So how does it look like? First, you see there is the red line is the calculate surface all, and the calculate surface all doesn't access the visible member of the class. So the padding between the visible and the point 1 and point 2 doesn't matter. So if size of the padding is in bytes, so the size of padding doesn't influence performance. But for calculate surface visible, when the padding is 0, when the padding is 0, then when the padding is 0, then it's the fastest, about 200 milliseconds, but as the padding grows, for example at 64 bytes, then we go to 250 milliseconds. So if we are accessing member of the class together, we should also declare them in the class close to one another. If we don't do that, then we are decreasing the data cache hit rate, and we are making our program slower. So why is processing of smaller classes faster? This is the explanation. So the data is brought up from the main memory to the cache memory, typically in blocks which are 64 bytes. So when your program needs, when the CPU needs data, it doesn't get from the memory only 8 bytes or 16 bytes. It gets the whole block. With large classes, the CPU is bringing data from the main memory to the cache memory that the program is not using. So you get block 64 bytes of memory, but when the class is size, you don't access most of these bytes that are brought from the memory. This wastes memory bandwidth and slows down your program. For code in the hot path, you should move all non-essential data to other classes, and this will help performance. So if you have a big class, making it smaller, moving out everything non-essential makes it faster. Additionally, data members that are often accessed together should be declared in the class definition, so declare them after one another. This increases the chance that the data members will land in the same data cache block. If they're in the same data cache block, access to one will automatically result the whole block is fetched to the data cache, so the access to another one, to the second one, is fast. Here is the small versus large classes memory layout. In the orange you see a cache line, visible is blue, P1 point is green, and unused data members is white. So if we have here a small class, we have a small class which has a visible endpoint, you see here, and these underneath how they map to cache line. And you see here that the first instance fits the cache line 1, the second fits cache line 1 and 2, the third one fits cache line 2 and 3, the fourth one fits cache line 3 and 4, etc. But the good thing about this is that we are using all the data that the CPU has brought from the main memory. We are only using all the bytes. Next, we have a large class with unused memory at the end. So this is a large class. It also has visible endpoint, but it has unused memories at the end. So we are loading, accessing visible endpoint 1. So we have here, below, the first class fits the cache line 1. The second fits the cache line 2 is unused. Cache line 3 and 4 fits the second instance. Cache line 5 and 6 fits the third instance. So all these bytes that are brought from the memory are not used, it's wasted memory bandwidth, and it slows down your program. Similar is when we have large class with unused members at the end. See what happens here. So we have a visible and we have point. So the CPU brings visible member, but all the cache line, all the rest of the data is never accessed. So this point 1 is not, so the access to the point 1 is, data point 1 is slow because it needs to be fetched from the memory. And you see the visible fits one cache line size, one cache block, point fits another cache block, visible fits another cache block, so this is much slower than this layout. We talked about array of pointers, we talked about class sizes. What are some other ideas for optimization? So if you have a random access structures, trees and hash maps, they will definitely benefit from improved memory layout. First thing you should know, for all random access data structures, if you keep the block of memory used by the data structure as compact as possible, this increases performance, as you have seen for linked lists. These kind of data structures are called flat data structures. If you can look it up on Google. In case of binary trees, you can use a better memory layout. You should look up 1M, the Boas layout, which is the best memory layout for binary trees. It promises the best performance. Or you can use n-ary trees instead of binary trees. N-ary trees are typically more cache-friendly. If you have problems with performance of hash maps, you can switch to more cache-friendly implementations, such as hash map with open addressing. STL implementation of binary trees and hash map is not the fastest in the standard library, and there are faster alternatives like EA standard library. EA is the game developer. So we talked about optimizing. Now the question is when not to optimize. Some of the techniques presented will benefit only the cases with large data sets. So many optimization techniques, as you've seen with linked list, on small linked list, memory layout is not important. Binary tree optimizations and hash map optimization only makes sense if the data set is large. If you have large containers, it will probably not pay off for really small vectors. Small data set is, what is a small data set? Small data set is a data set that fits L1 cache, and on most CPUs it's the size 16 to 32 kilobytes. A large data set is data set doesn't fit the last level cache. On most CPUs, the size of last level cache is a few megabytes. So if you have a really large data structure, it will most likely not fit the last level cache. Data structures with a short lifespan also don't benefit from optimization a lot, because creating a memory optimal data structure can take more time than the average data structure. If the data structure is just used a few times and then destroyed, the overhead of creation can dominate the runtime. Okay. This closes the topic of memory performance and memory intensive codes. So what is the conclusion? For good performance, it is essential to use the available memory bandwidth in the most effective way possible. Avoid random memory access when possible. Prefer vectors. Avoid vector of pointers. Prefer vector of values. Keep things that you use together close to one another in memory. Keep data you're processing small, so keep the small classes you're processing small. Avoid rereading the same data from the memory several times. With a few exceptions, nowadays most software that you're writing and you're working on is memory intensive. Mobile devices typically have slower memories, smaller data caches, and less memory bandwidth, so this makes the situation even worse there. But with careful programming, a reasonable performance can be achieved even on mobile devices. That's it. Thank you very much. If you're interested in C++ software performances, subscribe either on Twitter or LinkedIn. If you need help with performance in your program, you can contact us. We do also performance consulting. So these are the addresses you should visit.
Thank you, Ivica, for the masterclass. And I'm glad to see technology finally focused properly. So
you're welcome.
So let's see. I think we have a couple of questions. Right. So the first one. This was really, like I said, a masterclass on how to optimize for performance. But I'm curious about your experiences. Like, what are some outlier experiences you've had? What is the biggest optimization you've done? Your big whale.
The biggest optimization, I mean, in the sense of performance improvement, is a loop interchange. I talked about that, and loop interchange. If you have a code that processing images or processing matrices, this can give you 10, 15 times the speed improvement. Also with the linked lists, if you manage to maintain the perfect memory order, then you can also get like 100 times speed improvement. But typically this would be much. So most of the time it's not that much. Most of the time is, if you manage to vectorize loop that wasn't vectorized before, you'll get improvement of about 2, 3, 4 times. And if you do some changes in the environment, then you get speed improvements 20, 30, 50%, not more than that. But it all depends. Often it happens that the reason for performance degradation, it's not like a problem in the hardware, but a problem in the language. For example, once a customer, they weren't using the hash map properly. They were initializing with a small bucket count, and that caused that, and they fill it with a lot of entries, and that caused that hash map had to be rehashed several times. So yeah, the problem was in the STL library. They weren't using it properly.
Wow. And when you looked at so I'm curious about mobile, because mobile, I think services are one classic way, but I'm looking, do you have any mobile experiences that you're like, wow, I never, what is your most proud optimization on mobile?
So normally I don't specialize in mobile, but mobile, I mean, the whole talk can be applicable to desktop computers, to high performance computing centers. But on mobile, you need to be careful of the energy. So some of the things that work on HPC, on high performance computing, don't work here. For example, you can have a multi-core application in HPC that scales really well. Like with 10 cores, it's 10 times faster. But on mobile, it scales with 4 cores, it's only 2 times faster. You ask yourself, what was the problem? Well, your memory bandwidth. So you cannot get that much data from the memory, and your all CPUs are running. So they're running and they're doing nothing. You want to avoid that. Okay.
No, thank you. That's really insightful. And I think we had the second question. Listen. All right. So you're doing performance consulting, so you get to look over lots of other engineers' shoulder at the code they write. What do you think is, among all the patterns you've listed, which is the one that people forget about the most?
So that depends a lot about, that depends on what kind of software code are you looking at. So I do a lot of I investigate a lot of HPC code, so I know these things that, but they always work with simple types. And sometimes because of pointer aliasing, the compiler doesn't generate the efficient code. That's one part of the story. Also, you see that similar types of code on mobiles, because graphic processing, video processing, audio processing, all these things work on with simple types. But object-oriented programming, the worst thing they do is they create a class that contains so many fields that most of them are unused. And then you start processing these huge classes, and then everything gets slower and slower. So this is let's see, in the object-oriented paradigm, the anti-pattern number one, large classes, the problem decomposition is not done correctly. This is on a low level. There are also performance problems on high level. I don't do that regularly.
No, this is This is super interesting. Thank you for your time today and for the really great talk and the insights from all your performance optimizations. Stick around for the panel talk in just a
Yeah.
few minutes. And now
Yes.